Okay, so for section 6.5, we are going to do the area between curves. In 6.4, we were looking at the area between the curve and the x-axis. This one, we're going to add in another curve, but let's just start by talking about that for a minute. So this review, we have the area bounded by the x-axis in the graph of y equals 4 minus x squared on this interval. So the x-axis is here. And the point that I'm trying to make is this is basically the same thing. Are we going -1 to 1? Okay, so from -1 to 1. So we're looking at this area here, but you can kind of see that this is the area between two curves, this being one curve and the x-axis being the other. But the way that we did this, remember, was we looked for any places where there were x-intercepts, and here there aren't any. So we can just evaluate this sort of normally. So the definite integral from -1 to 1 of the function, and then, increase and divide. And so you have 4x minus x cubed over 3. And this is evaluated from -1 to 1. When you plug in 1, you get 4 minus a third. And when you plug in -1, you get -4 plus a third. This altogether gives you 22/3. So the kind of the point here is that we looked for x-intercepts first. We didn't find any, so we didn't need to break up the integral into different pieces. And so the idea for this is going to be kind of similar. So you're going to look for any places where they intersect on your interval. So we have this still the same parabola, 4 minus x squared. And then we have this line, x plus 1. So again, we're looking at that same interval, but we want to know the area between the two curves. So that's just this area here. So what we're going to do is use the fact that the area between the integral gives us the area between the x-axis and the curve. So we would have this like big area. That would be the integral from -1 to 1 of 4 minus x squared dx. And then we would also have this smaller area here. And we're going to take that away. So minus the integral from -1 to 1 of x plus 1 dx. So this is the big area. That's not what I meant to do. So you're looking at a big area minus the smaller area. And that will give you just that shaded, this green part. It's the area trapped between the two curves, top curve minus the bottom curve. And so we would expect that this is smaller than 22/3. And when you work that out, it is 16/3. But you can kind of see this is 1, this is a half, and this is a half. So you're looking at 22/3 minus 2, which is 22/3 minus 6/3, so 16/3. So that's how you do the area between two curves. This is when the top function is bigger than the bottom function everywhere on the interval. So in this one, we're looking at f of x, and this is g of x. So top minus bottom. So that happens everywhere. And so so that's what you want to do, is basically graph it to see which function is on the top, and then do that. So the integral from a to b of top minus bottom. So think about that total area setup. That's kind of what we did before. So you're going to do area above the x-axis, and then we had the area below, and we did subtract that off, or we added the absolute value. So f of x minus 0, because this is the x-axis. So that would give you the top function minus the bottom function. Or the area below, you do top, which is the x-axis, minus bottom, which gave you the negative, sorry, that should be an f of x there. Top minus bottom, and that gave you, that gave you the absolute value of the integral because it was, the negative of that negative area. So this is the same kind of idea. You want to look at the graph and that'll help you sort of decide what to do. So we have on this one, let's see, x equals 2 to 5, x squared plus 2, and y equals x. X squared plus 2 and y equals x from x equals 2 to x equals 5. Okay, so there's a lot going on there. Let's get that. Well, okay. So put that here. And we can see that this guy, that the function on top, that's x squared plus 2. This function on the bottom is y equals x. And then we're going from 2 to 5. So we're going to do the integral from 2 to 5 of top minus bottom. So this is the integral from 2 to 5 of x squared plus 2 minus x dx. So that would be x cubed over 3 plus 2x minus x squared over 2, and all this evaluated from 2 to 5. When you do this, I have 235 over 6 minus 14 thirds. So 34 and a half. Okay, I'm not going to do the Desmos thing. I'll just show you what maybe I should do the Desmos thing, not this one. Okay, so we're looking again at x squared. Now we have x squared plus 1 and e to the negative 0.2x. X squared plus 1 and e to the negative 0.2, negative 0.2x. And then x equals 0 and x equals 4. Okay. Let's see here. What's going on in there? Anything? Okay. Oh, that's an interesting little thing here that the top and bottom functions swap, but that happens outside of our interval, so we're not really worried about it. But we have this intersection here, which Desmos is kind enough to give us this intersection here and here. I can't get it to show me both of those points. That's annoying, but okay, so we have that. Again, that the top and bottom functions swap, but that's outside of our interval, so it's okay. So we're not concerned about it. All right, let's see here. Let's use a different color just to get some contrast happening. So it looks like the top function here is x squared plus 1. And the bottom function here is e to the negative 0.2x. So we have the integral from 0 to 4 of the top function minus the bottom function. We're going to do the integral from 0 to 4 of x squared plus 1 minus e to the negative 0.2x dx. Now, maybe you've noticed, so the first part is just power rule or reverse of the power rule. The second thing, this would be e to the negative 0.2 dx divided by negative 0.2. So 1 over u times e to the u. 1 over u prime. But you could do a u substitution on that. So u would be negative 0.2x, du would be negative 0.2x dx. So 1 over du, this would be negative 0.2, no x. So negative 0.2 d, 1 over negative 0.2 du is dx. So then you could plug that into your integral, and this is what you would get. And then we are evaluating from 0 to 4. And when you do that, I have 22.58 minus 0 plus 0 plus 5. So 22.58. Okay. Another example, we have x plus 1 and x squared plus x. No intervals here. X plus 1 and x squared plus x. So we're going to look for intersections because we're looking for the area trapped between the curves. So we just want to look for where that happens. We're going to get rid of all that stuff. So if you can see here, the area between these two curves is here in this interval from x equals negative 1 to 1. Okay, so then we will go do this in our, go do this in our notes. So we're looking at the interval here from negative 1 to 1, and it looks like the line is on the top, so that's the x plus 1, and on the bottom here is x squared plus x. So we're going to do the integral, choose different color, green. The integral from negative 1 to 1 of top minus bottom. Here, that's the integral from negative 1 to 1 of x plus 1 minus x squared plus x dx. So then I'm going to simplify that before I take the integral. So x plus 1 minus x squared minus x, so those go away. So I have the integral from negative 1 to 1 of 1 minus x squared dx. So that's x minus x cubed over 3, increase and divide, evaluate from negative 1 to 1. When you plug in the 1, you get 1 minus 1/3. Plug in a negative 1, you get negative 1 plus 1/3. So negative or 2/3 minus negative 2/3, so 2/3 plus 2/3, which is 4/3. Okay, so that is area between curves, and yeah. Let's see if we can do consumer and producer surplus here as well. So this is an application of that idea. So for consumers, what does the demand curve represent? The demand curve is the price consumers are willing to pay. And then the supply curve, though, is the price at which producers are willing to sell their product. I should mention this, there are no examples in here of this happening. Let me draw a picture though. So suppose that we had, let's see, where could I do this? Get some space. Suppose we had something like this and we wanted to find the area between the two curves. Something like this. So this is, let's say, let's do this in a different color so we can tell what's going on. This is f of x here. And then this guy is g of x. So say this happens at 2, this is at 5, and this is at -1 or something. So what you would do is the integral from -1 to 2 of g of x, because that's the top, minus f of x. And then you would split this up. So the integral from 2 to 5 of top minus bottom there, which would be f of x minus g of x. So I hope that makes sense. We didn't have any examples where it broke up, where it like split up in the interval that we were concerned with, but that's how you would do it. Find the intersection point. So look at a graph in Desmos or wherever, find those intersection points, and then split up the integral however you need to do top minus bottom. So if the top function switches like it does here, the top function switches from this green one to this orange one. So then you need to split the integral there too. Okay, so I think I will stop the video there, and then I will come back and do the consumer surplus. I'll just do all the applications, consumer producer surplus and Lorenz curves, in a different video to make this more digestible.